So the basic idea is very simple. We want to send generated input to a program that we want to test for bugs or security. And while we're sending those inputs, we watch how it behaves. So that's really like contained of two main parts. So for one, this generating inputs and sending them to the application. That's something where fuzzers have become ever more sophisticated, and that's sort of a very highly developed topic inside academia. And coming from the C, C++ environment, there's been a lot of focus on, okay, how do we generate interesting inputs so that we can test or generate test cases that are interesting and get us deeper into the code, because that's what it's all about. That's where the bugs lie. And another thing that the fuzzer will do, it will evaluate inputs and then schedule the interesting ones for further mutation. So it takes these inputs, mutates them, targets the application again. And another thing that fuzzers or a good fuzzer will do, it will detect if the data needs to be structured in a certain way to basically get deep into the code. So for example, if your application processes JSON, it will automatically detect that JSON is the data to send this application, and then generate inputs that actually do trigger interesting behavior in the code. And that's the second part. We want to watch what's happening inside the application. So one thing we could look out for is crashes, but then also memory safety violations. That's sort of coming from the C, C++ background. That's where a lot of bugs lie. And address sanitizer is a very important development there, which basically it detects most of those memory safety violations and can report them early so that these bugs can be fixed. But this is not like these bug detectors that check for memory safety. They're not limited to memory safety, but we can basically introduce arbitrary code inside or inject it into the program to check for various other kinds of bugs. So one example would be we can write a bug detector that checks for SQL injections as they are happening, and then we rely on the fuzzer to trigger those injections. Then what the fuzzer also usually does, it keeps track of special functions that have been called. Like a good example is when two strings are compared. You can note down one of the strings, the string that it's being compared to, and the fuzzer can use this to generate new inputs that might pass the string compare if it's happening inside an if statement. And maybe most importantly is the fuzzer keeps track of how far into the code each input went. So that's basically how the fuzzer will evaluate each input. So it tries to maximize for code coverage, which then is a good signal for, okay, we have higher chance to detect interesting bugs. Again, here is sort of an illustrated example how this might work. So a good example is an image parser. So we instrument this. So we inject these hooks into the application to get the fuzzer this feedback. And then the fuzzer can, even with a simple 0 byte, it can start mutating this byte. And through this feedback that it gets from the instrumented application, it will generate inputs that are more and more sophisticated. And what will actually happen if you fuzz an image parser is that at some point it will produce valid images. So from 0 byte just through mutations, these covered guided mutations, it will end up with an valid image. So fuzzing has now been established quite well in the C and C++ community. So I would say it's indispensable there. I certainly wouldn't trust a C software if it isn't fuzz tested. And there is this common misconception that fuzzing is only it's restricted to the memory unsafe languages, that it only makes sense to fuzz those. But okay, so there is some point to this, because memory corruption is often very critical, and if you find one of those bugs, it's you should fix it as soon as possible. But all the other bug classes, they're basically still out there, and they're also valid in memory safe languages. So there is many projects that target memory safe languages for fuzzing, but this has been a recent development in the last few years. And we also have our fuzzer that we open sourced this year. That's the Jazzer fuzzer for the fuzzer for the JVM. And this has been recently picked up even into the Google OSS Fuzz project. So to my knowledge, largest scale fuzzing initiative run by Google to test open source projects. And what we found is that Jazzer is really, it has a very high success rate. So every project we onboard, we find bugs in there. And just this year, we have found we have found hundreds of bugs in many open source projects that are now onboarded on OSS Fuzz. And this just shows that fuzzing inside the JVM, or generally memory safe languages, is sort of an unexplored topic, and there is a lot to gain from adding fuzzing to those languages. Okay, but now coming to the challenges of fuzzing web applications, there is still something that it sort of makes life hard right now if you want to perform fuzzing on your enterprise web application. So many times it's hard to find a single function which should be targeted for a fuzz test. So traditional fuzzing, you would write a piece of code that directs the input from the fuzzer to the function that you want to test. But for a big web application, this there might not be a good candidate for this one function. So if you have an image parser in there, that would be great. You can target this. But if you have a complex API with many endpoints, that's sort of hard to find this one function that you want to send the fuzzer input to. And also the inputs are in most cases, they're very highly structured, but also complex. So you might have a REST API or a SOAP, or you have a gRPC API. So there is usually something that describes this API, and then this knowledge, it should be known to the fuzzer. So it's so that the fuzzer can target, it can generate inputs that respect this API, and then have a high chance of actually reaching the application. Another challenge with testing web applications is that traditional fuzz tests, they are normally a single compiled binary. That means that you basically fuzz one JVM instance, or you fuzz one piece of code, but that's simply in many microservice environments, or environments where you want to test the interaction of multiple services, that just doesn't cut it. And testing those in isolated environments is often quite hard. So, and there's really right now, there is no good solution for this. So currently you would have to write basically a fuzz test for each microservice, test them all individually. And then another challenge that often comes up is that these applications are run in a different or very diverse environment. So for example, you could have your microservices running inside a Kubernetes cluster or generally in Docker containers across multiple hosts. And just sort of an unexplored, so fuzzing is usually not performed in these kind of environments, at least not for multiple services. And those sort of problems we came up a lot like during the work at Code Intelligence, and we decided so many customers are having this problem, so we want to address all of those problems, which led us to like developing a new kind of fuzzer that's included in our latest release, the release 220 of CI Fuzz. And basically we started by disconnecting the fuzzer from the service, from the software that it's testing. So here you can sort of schematically see we have the services under test. There are like 3 services in this case, and they're running inside some kind of environment, let's say Kubernetes. And now we have the fuzzer, which is external and simply sends HTTP requests. So it behaves like a client. And so far, it just looks like basically a black box fuzzer. So the fuzzer just sends requests and knows nothing about the application. But we want to have this feedback loop that's quite essential for the modern fuzzing approach. And we get that by adding Java agents to each of the services that we're interested in. And they will send back the fuzzer this feedback that it needs to perform better mutations. Okay, so that's the basic idea. And I want to briefly show you how to set up such a fuzzer and how to find bugs in a fairly complex web application. Okay, and with that, I will jump over to VS Code. Here I have checked out the Corona One app server. So that's the backend for the COVID tracing app that you might have on your phone if you're from Germany. Let's go to the browser. So this is the project that I mentioned. I simply checked this out. And because I know that the current version is quite well tested, I checked out an older version from last October, which I know has a flaw in there. And okay, let's get an overview of this architecture by going here through the docs. So this would generally be the first step in assessing how a fuzzer could work in this environment, how like what services are a good candidate for fuzzing. So I'm going to look here at the architecture, and so this is the project that I've checked out locally. So there is like a submission service, and then some other stuff. And here I see those 3 services here. They're run by cron jobs. So that's not ideal because I want the fuzzer to generate an input and then something should happen in that service. So like my first instinct would be to like ignore those services, but focus on the submission service. And then the submission service, it will send requests to the verification server. So this is basically the interaction that happens if you test positive, you get your lab results back, you click on the button to notify others, and you will send this ton and whatever test result you have. And this will then be verified by the verification service. So this is the flow that I would like to test for now for a quick setup. So that means two services that I would be instrumenting here, the submission service and verification service. Okay, let's go back to the project. So they provide a fairly easy way to start all of this backend. They have a Docker Compose file. If you're not familiar with Docker or Docker Compose, it shouldn't be too terrible because like it just describes how these services are started, and basically they're all running in isolated environments. So in here I have the submission service, which is what we're going to test, and then also the verification service. And here they supply a fake, like a mocked version of it, but like this kind of fuzzing is all about the system test level of fuzzing. So I don't really want a mock version in here, but I want like the fully fledged verification server. On this Docker image I prepared earlier, so I also cloned the verification server project and built that Docker image. So let's get up here and search for fake. And now I'm a bit closer to the more realistic case of running this backend. And I've already built those Docker images, so I can now just run them. And this will start all of this, like the whole backend, including the verification server. Okay, it should be up now. And what I also prepared earlier, I got an HTTP request that sends a message to this submission server. So you can see here there is the 10 that have to get completely right, and then the post body, which is like a not too complex JSON structure, but there is already some data in there. So if the fuzzer were to completely ignore this this API definition that we have, it will never construct this kind of message. Okay, and we can test this out by, okay, apparently it's not up yet. Okay, I get a 500 back. I think that's because one of the services is taking a bit longer to start. Okay, now I get the 200 back, so that's so my application or this backend is now fully running. And okay, now I want to prepare it for the Fuzz test. So the way I do this is that I first of all go into this Code Intelligence extension and create a blank project. So I'm just using this project for web application fuzzing, so I can do a very quick setup. Okay, now this project is initialized and I can start adding or preparing those web services. So if you remember from the previous schematic, it's basically about adding a Java agent to the services that I want to test. And there is here some helper to make this as easy as possible. So here I will give it an identifier. So we're testing the submission server first. And then here I will pick a package for the fuzzer to only instrument classes that are under those package. So that's quite useful if you want the fuzzer not to get lost in some other library. For example, if I want to like primarily focus on the code that is written in here, like the code from the Corona 1 app, then this makes sense. Otherwise, the fuzzer might also target the Tomcat server itself or the Spring framework and might get lost in there. Then another configuration I will have to do here is because the service is running in a Docker container, I can't reach the fuzzing backend, which is running locally here for me. I can't reach it on localhost, but I can reach it over the Docker network. So I will get the IP address of the Docker host and paste that in here. And what I get here to copy is basically an argument for the Java command line. So if I were to run the submission server here in the command line, I would simply type in Java and then paste this argument in here, -jar, and then submission jar. But here we're running inside the Docker environment. So we have to find where this Java command basically is configured for inside this Docker environment. So if I look up here, the submission service, we see, okay, there is a Docker file which defines the service, and I can jump into there. So this basically defines in what environment the submission service runs and how it is executed. And down here we see this the Java command that is being executed. So there is already some options to the Java arguments, and I will simply paste in here as another argument what they have in the clipboard. Okay, and that should almost do it. However, here inside this container, this fuzzing agent, it won't be available because this is an isolated container and it doesn't have this file that I have locally on my machine. So what I do is basically I copy it from another image. Here I provide another base layer for or basically multi-layered Docker build, and then I can copy it from that Docker image. Okay, so in this Docker image, I know there is this fuzzing agent deploy jar, and this fuzzing agent I simply copy here into the working directory. So that should be it. I will quickly build this service. Of course, there's other ways how to get this this agent inside this Docker image. So I could have just copied it from my local file system, or also mounted it inside volume. So a lot of options to add it. But this here has the advantage that whenever there is an update to the fuzzing agent, you can simply rebuild the Docker image and pull the fuzzing agent again and get all the updates. Okay, for some reason it's downloading some Maven dependencies again, but that should be done fairly quickly. And that's really all there is to it. So basically to prepare this service for fuzzing, simply add the fuzzing agent. And okay, now that this image is built, I will start all these services again, or it will now only update the submission service. And going back here to the extension, We can wait a little bit. And here now register this submission service. Okay, now I will do basically exactly the same, but for the verification service. So let's get another command line to copy. I will choose a different name, but all the other arguments, they can be the same. And then inside a new window, I will open the verification service. Okay, and here I have the Docker file already open. I basically do exactly the same steps. So here in the entry points, I will add as another Java argument the Java fuzzing agent. Also here, the path is not entirely correct, so it won't find it currently in the container. So I will also add the base image CA fuzzing agent and copy the agent from there. I built this Docker image. Okay, this is done quickly. I can close this window already and update the services. Okay, wait a little while, and here it registered. Okay, now we can almost start fuzzing. One thing that I want to configure is that that the submission service, we have an open API definition for it, and I can specify that. This is just like the extra information the fuzzer needs to generate good JSON data. So otherwise, this would be like wild guesses that okay, a transmission risk level is of type number and is nested here inside keys. But like supplying this open API definition, the fuzzer can specifically like take this into account and generate inputs that make sense, and sometimes also those in the edge cases that don't make sense. Okay, and in here we have just this one endpoint that we're gonna fuzz now, which is like this sample request. And okay, so this is now like mostly configured. We can add fuzz tests. There are different kinds of fuzz tests you can create here. So this API fuzz test would be sort of a standard Jazzer fuzz test, but here we want to create a Java agent fuzz test. We give it a name. And then say that we want to fuzz both these services, so the submission and verification. Then hit save. And this will have created a few files on in this project directory. So inside the .code intelligence folder, there is now fuzz test with a YAML configuration. Here we also have this information that submission and verification are tested. And here we'll correct the base URL because it's not running on 8080, but on 8000. And what also happened automatically is that it generated some seeds for the fuzzer to use. So if you remember the example from the image parser, this is basically the 0 byte that was provided there. If you already start with a valid image, then the fuzzer is much quicker to find its way deeper into the code. So if we start here with a good initial request or with a good seed, then the fuzzer is much quicker at actually finding the interesting cases and doesn't have to first figure out how to reach the API. And so here are a few like automatically generated seeds. It's also got seeds for this verification service. So it will try to target like the test result, for example, from the verification service. But for now, I will simply delete all of those because we already have a pretty good seed in here, this request that I constructed earlier. So I will move this into the seed directory for this fuzz test. Okay, and that should be it. Verified it still works with the instrumented services. So we get a status 200 back. That's good. And then I think we can start fuzzing. Okay, so I'm back now in our extension, and this is the configuration for this fuzz test we created. And now I can simply hit run, and it should start fuzzing these two applications. Okay, wait a bit for the applications to reach the fuzzer. And now you see those are coverage metrics. Those are they are going up. So for you who know a bit about like these fuzzers, this is libfuzzer running under the hood, but it's getting the coverage feedback from these two services. So transmitted from the agent to the fuzzer, and then libfuzzer processes this. And we then have a custom mutation engine, and also, of course, this fuzz target entry point, which sends the requests to the services. So as long as the numbers are going up here, that's all good. So from this one seed, it already created 40 different requests, which basically all have different all reach different code paths inside applications. And we can take a look at what the fuzzer found so far. So we have here the findings that I was interested in, which is the reason I specifically checked out this version of the Corona 1 app backend. So we have the fuzzer found here an expression language injection. You can take a look at where this happens. So this is basically when validating the post data, this function here is used to construct a good error message when a constraint inside this post data has been violated. So maybe your message was too long or not of the correct format. This function will write a message for that. However, the problem is if you're using default configurations, this is interpreted by the expression language interpreter. So, and we can look where this add violation is being called. It's being called, for example, here, check origin country is valid. And in here, like the string that is being sent to this function is inserted with something that's directly from the JSON payload. So an attacker has like a direct control over the string, and that's a problem if we're evaluating this expression language, because that basically gives you a complete code injection. We can take a look at some examples for this expression language. It basically helps you to inside these template strings. But as you can see in here, there is actually code being executed, and you can also execute functions in there, which is what the fuzzer managed to do. So it's if we look at the exact exception here, it actually managed to call a function inside our fuzzer, which should never be called, and this leads to this injection. So there is some other stuff that the fuzzer found, some exceptions that lead to 500 errors. So those are probably not security relevant, but there are still bugs. So things where here a request is being sent to the verification server that is invalid, and then triggers a 500 error inside the submission service. So this might not be too security relevant, but it's still bugs that you want to find. And you can see here that the fuzzer is actually quite good at finding like obscure things. So in here it replaced the number with strange symbols, which also erased 500 error. And okay, and since we have a bit of time left, I would like to quickly fix those two injection bugs, and we can run the fuzzer again and see that they have been fixed. Okay, let me stop the currently running fuzzer. Okay, and this is the class that validates the post body, and from the findings, we can see that okay, here inside the origin country, we can inject, and also inside visited countries. So those are like two instances where we have to correct the code. Okay, here I would simply correct it by not printing the origin country, the input from the user. Okay, and here as well. So now the user input shouldn't reach this function, which is then interpreted by the expression language interpreter. Okay. I think that already fixes the issue, so I will build the container again. Let's see if it does the exact same Maven downloads again. It does. Another nice feature is that you get code coverage from all the services that are instrumented. So this, like, we're only testing this one API endpoint right now, so it's not getting like full code coverage, but 27% I think is already quite good for like this quick setup. And this is over like all the classes that have been like instrumented and that are also in this app.corona1 package. Okay, so this has built. I will update the service. Okay, and then wait a bit until they're running. You can test this with this request. You can also look inside the logs of the submission server. And here you can see that that we're getting some from the Java agent, the fuzzing agent. We're getting these notifications that it's instrumented some classes. So it's mainly instrumented app.corona1 classes in here, but then also some others. For example, in the Spring framework, where we're specifically hooking certain methods for these bug detectors. Okay, I think it should be running now. Okay, we get 200 back, so let's start the fuzzer again. Okay, and now it will stay at these 3 findings. And another thing you can see here, it already starts with this corpus that was built up during this fuzzing run. So here it took some time to get all these inputs, but here it's reaching those inputs quite a lot quicker. And then, okay, it seems like the fix actually worked and we don't have this injection anymore. Okay, that's what I wanted to show you in terms of live demonstration. So let's hop back to the slides. Okay, to give a brief summary, so what we did is, like, first we looked at the architecture of this backend that we're testing and identified what services make sense for fuzzing. So these cron job triggered services didn't really, but there were 2 that made a lot of sense because they're running together. And then we added basically this instrumentation capability by adding the fuzzing agent to the Java start. Then quickly configured the fuzz test and also gave an HTTP request as a seed for the fuzzer to get started. And that was basically it. So then simply starting the fuzzer and waiting until all the bugs have been collected. So that's it for this demonstration. And I would say we could open it up for the questions and answer. Okay, no questions so far. I'm just getting a thank you. Jacob, do you have some questions for me?
None so far, but thank you for the presentation. That was really interesting. So yes, I would say if there are no further questions from the audience, we can close it right here, and yeah, everyone will get the recordings afterwards. So thank you, Simon, for your presentation, and yeah, I hope to see you next time again.
Yeah, thanks to everyone participating.